Okay, so let us start with this very important concept, which is thermal properties. Which are the thermal properties? We have dealt with physical and chemical properties. We are dealing with physical and chemical properties. We discussed about rheology. We discussed about color and optics. We discussed about structural relaxation and rest of the things. Now we are coming on to thermal properties. These tables are very important and the data derived is also very important. I'll deal with it a bit later. Let us first start with your thermal properties. The first question, as always, why do we need to study thermal properties? See, whenever there are, let's say, deep cavities. What do I mean by deep cavities? Let us say this is the tooth and I have pulp inside it. I have pulp inside it, and this cavity, this caries, is coming here, very near to pulp. And I have filled it with metal. I have filled it with metal. So the heat, if I have filled it with metal, the heat will reach pulp and cause damage. This is one of the aspects that must be kept in mind. So in this case, heat transfer is very bad. We do not require it. So we will be using metals in which heat transfer is not good, or we will be providing an insulator beneath it. What is an insulator? We'll talk about it. Otherwise, you also know what is an insulator. In certain cases, it is advantageous to have heat transfer. Can anyone tell me what will be the advantageous situation? Anyone from you? No. See, I'll tell you. So in case of a denture base, whenever we are providing denture to the patient, heat transfer is very important, because in that sense we require heat transfer to the mucosa, so that we can sense when something hot is coming and when something cold is coming, or thoda bahut taste sensation के लिए भी can act as a protective response. So then it becomes an important property. Okay. Also, you must remember that whenever something expands, means whenever the temperature is increased, there is a propensity to expand. And whenever the temperature decreases, there is a propensity to contract. This is very important. Okay. This must be taken into consideration. Why so? Because let us assume that we have provided a filling to the patient, and because the oral cavity is a very volatile kind of an environment where the temperature changes very rapidly. Let's say the patient is sipping a 60 degrees Celsius tea, or maybe having an ice cream which is up to 1 or 2 degrees. So the filling can expand and contract and lead to marginal gaps. Now whenever there will be marginal gaps, there will be something known as marginal leakage, or a better term is micro leakage. And this micro leakage is responsible for secondary caries, means the caries which is happening once the previous caries had been removed. Okay, this is important to understand. Now there are two properties that are very much important whenever we are talking about thermal conductivity and diffusivity, which are, let me just check whether the recording is happening fine or not. Oh my god, I'm really sorry for that. I think it was way too zoomed. Anyways, now it's better. So there are two properties which are thermal conductivity, and the other property is thermal diffusivity. Firstly, we'll discuss about thermal conductivity. So let us assume that we have a rod. Which is having an area of 1 centimeter square, cross sectional area of 1 centimeter square, and the thickness of the rod is 1 centimeter. Again, thickness is 1 centimeter, and there are 2 points, point A and point B, the start point and the finish point of the rod. The temperature difference between the two is 1 Kelvin or 1 degree Celsius. Okay, so the quantity of heat of heat in calories per second getting transferred is known as thermal conductivity through this setup. The quantity of heat getting transferred from a rod which is 1 centimeter square in cross section, having a thickness of 1 centimeter and a temperature gradient or temperature difference being constant at 1 Kelvin is called thermal conductivity. It has been observed that thermal conductivity of polymers is less than ceramics is less than metal. Obviously, metal will be a good conductor of heat, whereas polymers and ceramics will be poor. Polymers, you can say plastics. So plastics will any day have a very bad kind of a thermal conductivity as compared to ceramics. Okay. Sure. This point is covered. Now let us go to this point. Anyone, what is a conductor and what is an insulator in terms of conductivity? Okay, something is having high conductivity. So will it be a conductor or an insulator? Yes, good. And what about insulator? Low conductivity. Good. Okay. So now understand this particular phrase given in Phillips. If thermal gradient or the temperature difference gradient, which I mentioned 1 Kelvin between the 2 points of the rod, is constant and does not change, means heat supplied and heat withdrawn is in equilibrium, so that this temperature gradient is maintained at, let's say, 1 Kelvin or 2 Kelvin or 3 Kelvin and not changing with time, then thermal conductivity is measure of heat transfer. But if this gradient is changing, then thermal diffusivity becomes a more important property. Okay. Now coming on to thermal diffusivity, let us discuss thermal diffusivity. If we have come this way, it is the speed with which temperature change will spread through an object when surface is heated. So it's not the quantity of heat transferred or anything, it is the speed with which temperature change occurs. Now, to make you better understand the phenomena, let's say there are 2 points A and B. Okay, the speed with which a car travels from A to B is known as diffusivity, and the amount of people carried by car at a time is conductivity. Okay, you can understand it this way. Now diffusivity has a formula. Conductivity upon heat capacity at constant pressure into temperature dependent density. So heat capacity at constant pressure has another terminology which is known as specific heat, is the other name of this thing, and time dependent density. Conductivity is represented by kappa. Heat capacity, let us call it as Cp at constant pressure into temperature density dependent density, which is denoted as this Greek P. Now, if I ask you from this formula, what will happen if I increase the heating capacity at constant pressure? What will happen to diffusivity? Well, obviously, if this relation is inverse, so if we will increase Cp or this density, diffusivity will decrease. And whenever I increase the heat and density, decrease it, the diffusivity will increase. Now let us come on to the tables, or let us take the tables at the end. Okay, let's discuss the concepts first. So पहले तो हमने ये discuss कर लिया. Now there is another concept known as coefficient of thermal expansion. Let us say we have an object named A. I supply it temperature. मैंने इसे temperature बढ़ाकर दिया, मैंने इसे गर्मी दी, तो energy is being supplied, vibrational motion happens, interatomic distance increases because of the vibrational motion, and expansion occurs. Chalo. Let us understand it this way. We have Shubham in class. He is not at all working. He is very lazy. He is not coming out of his bed. He is just staying stagnant. Not at all working. मैं अचानक से जाता हूँ और शुभम को बोलता हूँ that there was a girl who was talking about you in canteen. अब शुभम क्या होगा? शुभम को मैंने प्रोवाइड कर दिया एक स्पार्क, यानी कि एक टेम्परेचर या एक हीट. अब शुभम होगा एक्साइट. शुभम एक्साइट होगा तो मोशन आएगा, यानी कि मूव करेगा इधर से उधर. कैंटीन जाएगा, कैंटीन में 4 लोगों से पूछेगा कौन लड़की बैठी थी, फिर गार्ड से पूछेगा कौन लड़की बैठी थी, एंड पूरे कैंपस से पूछेगा कौन लड़की बैठी थी. धीरे धीरे वो इधर से उधर भाग रहा है, जिसकी वजह से शुभम का जो डिस्टेंस है वो एक्सपैंड हो रहा है. That is what happens here. I hope you understand the concept. So the change in length per unit of the original length by providing 1 degree Celsius is known as coefficient of thermal expansion. Now the marginal leakage is very important here. Let us say I have done a filling, class 2 filling, means the tooth was carious on the proximal side and I have filled it using a material known as mercury or amalgam, and I heat it. Increase the temperature, decrease the temperature, increase the temperature, decrease the temperature, bar. Now what will happen is the material will start to expand. A gap will be created here. This gap is responsible for marginal leakage. It has been found that direct restorative materials have 4.4 times more coefficient of thermal expansion than enamel, जिसकी वजह से there are chances of micro leakage. What are direct restorative materials? Those restorative materials which are directly placed in the oral cavity. What are indirect restorative materials? These are the restorative materials that are firstly prepared in laboratory and then taken into the patient's mouth. Now understand this another concept, why coefficient of thermal expansion is important. Let us say I have this metal coping. What is a metal coping? In a porcelain fused to metal crown, The metal framework or the metal substructure is known as metal coping. Over this, porcelain is painted and then put into a furnace so that it sets. This is the ceramic that is applied over it. Now I take it into a porcelain firing unit and increase the temperature. Because the temperature is increasing and reaching up to thousands of degrees, what happens is metal starts to expand. Metal starts to expand. Now because of this expansion, ceramic also starts to expand. What will happen if the coefficient of thermal expansion of ceramic and metal are not in equilibration? Metal will expand more, ceramic will not expand that much, and a point will come when metal, because it is expanding and expanding, ceramic it is not expanding, the ceramic will break, fracture. That is the problem. Now when I am bringing this to a cooler state, metal will try to shrink. Now if metal will try to shrink, composite will also, or ceramic will also come back. If this coming back is not in synchronization with the metal, again there are chances of failure of the porcelain fused to metal framework. So it has been recommended by Phillips that the coefficient of thermal expansion of metal and ceramic must be in the range of 4% only, not more than that. 4% तक का difference चलेगा, उससे ज़्यादा नहीं होना चाहिए. So this is all about the thermal properties which I was mentioning about. The first table which I have here is the density and thermal properties of water, enamel, dentine and dental materials. Density, specific heat, thermal conductivity and thermal diffusivity. As I have already mentioned, thermal diffusivity is equal to thermal conductivity divided by the specific heat into density. This must be kept in mind. So whenever we will be having a greater thermal conductivity, thermal diffusivity will increase. That is one of the trends that is seen in the table. Also, when density and specific heat will be increasing, thermal diffusivity will decrease. Okay. Now what all things can be inferred? I have written out all the important points so as to make you understand that how to read the data from dental materials textbook. See, firstly, density. Enamel key is greater than dentine. One thing established from the table. Amalgam and gold are extremely dense. Hence, their radio opacity is more in general practice. Composites are close to the tooth in terms of density. Better aesthetics and tooth-like feel comes with composite. Higher density has a higher radio opacity and metal show up bright white on radiograph. Composite resembles dentine and enamel. This is the inference from density. Now coming on to specific heat. Water has 1, which is the highest. Tooth structure has a low specific heat, enamel and dentine. Metals have extremely low, 0.03 and amalgam 0.005. Meaning materials with low specific heat up quickly. So metals heat up very fast with low specific heat, as you can see 0.03, 0.005 can cause pulpal irritation. Tooth tissues heat slowly due to water content and therefore your pulp is protected from dentine and enamel by the presence of dentine and enamel. So while polishing metal restorations, you must keep this in mind that the friction generated is heating the metal, and because the metal is being heated, it is causing damage to the pulp because the thermal conductivity is very high, specific heat is very low. Now coming on to thermal conductivity. Gold has an extremely high thermal conductivity, 297. Amalgam is 22.6, enamel is 0.93, dentine 0.57. Learning the numerical data is not the point here. Understanding it is the point. Metals, because they conduct heat, they need insulators. Amalgam and gold conduct heat, always place a base or liner in the deep cavities. Enamel and dentine have low conductivity, so they are protectant. So therefore we say that the amount of dentine thickness determines how much your pulpal health will be. If the thickness of dentine is reducing, you would have to provide a base below the restoration, especially amalgam restoration, so that heat is not transferred to the pulp. Now coming on to thermal diffusivity, gold has a very high thermal diffusivity, water has the lowest. Heat shock and metallic restoration is nearly instantaneous because the speed with which heat reaches, which is actually thermal diffusivity, is very high in gold. जैसे ही गर्म चीज टच करेगी, इट विल इंस्टेंटेनियसली रन टूवर्ड्स पल्प. बट वाटर का ये बहुत लो है. मतलब अगर आप वाटर को एक तरफ से हीट करते हो, दूसरे पॉइंट तक इतना जल्दी नहीं पहुंचेगी हीट. And as always, tooth tissue slow down heat transfer. See, all this we have learned, that high conductivity and low specificity. Now coming on to table 2, or the second table. Second table is talking about coefficient of thermal expansion of dental materials compared with those of tooth enamel and dentine. We are having this coefficient of thermal expansion, and then we are plotting a graph, or we are just dividing the coefficient of thermal expansion of the material and the tooth enamel. Different materials have been taken. Dentine is there, and then aluminous porcelain, commercial pure, all these, and then tooth enamel is there. Rest of the things are basically your direct restorative materials, mostly. Inlay wax is an exception. Most of them are direct. This is indirect. Let us dive deeper into this table. Materials with coefficient of thermal expansion close to enamel, which are a good match: enamel, GIC, titanium, dentine, and porcelain. There will be least interfacial stresses because as your enamel will be expanding or dentine will be expanding, these materials will also be expanding in a similar manner. Marginal seal will be really good, and porcelain, and titanium, glass ionomer and titanium integrate well with the tooth. Now materials with moderate mismatch: gold, palladium, pure gold, and palladium silver, slightly higher expansion, so but it is still acceptable. Now the materials with high mismatch: amalgam, composite, denture resin, pit and fissure sealant, and inlay wax. So they are bound to have a lot of marginal leakage, polymerization, shrinkage, and everything adds up as well in composite especially. Sealants, highest coefficient of thermal expansion. Heating, cooling may lead to debonding. Denture based resin, inlay wax, huge expansion, must be invested immediately. This is what is to be inferred and how you have to infer the tables that are provided in Philips.